All right, guys. So when we talk about pH, which is basically our percentage or our potential hydrogen, what's happening here is we have our water molecules. So we've got our oxygen, and it's got the two little hydrogens attached. Now, these water molecules in regular liquid water, they're zinging around, they're crashing into each other, and every now and then a hydrogen pops off. And then we have OH minus, because remember, oxygen's super greedy. It's going to hold on to that electron. And the hydrogen that only had that one electron, now it's hanging out as a bare proton. So it's going to be this positive H moving around, and we've got our OH that has the extra electron, so it's going to have a negative charge. Now, that's water. And when this happens, it's even, right? One OH minus, one H plus. Now, other liquids can have different quantities, right? It's not always even. When something is an acid, it means it has more positive charges. It has more H pluses floating around. When we have a base, we have more OH minuses. There's more of a negative charge. When we measure how much hydrogen is floating around, we refer to it as pH. P for percentage or potential, and the H for the hydrogen content. Now, we could have, in theory, measured the POH, but it's harder to measure, so that's not the one that they did. So they measured that hydrogen. Now, water is polar. We've talked about this the last couple ones as we talked about properties of water, right? So that oxygen's really holding on to those electrons. Those hydrogens, they don't have as good of a grip on the electron. They're trying to hang on to their one. They have a slight more positive. Every now and then, again, they split. We get OH minus and that H plus. Now, this occurs 10 to the negative 7% of the time. That's 0.0000001% of the time. Not a lot. Okay? However, that 10 to the negative 7% of the time is how often water splits, and that we have even charges. So some substances, again, have more H plus, some have more OH minus. Now, if you are anything like me, you don't like messing with exponents, certainly not negative exponents. It makes all of our math really difficult, makes it complicated. I hate typing them. Biologists as a whole, not a huge fan. So rather than having to have all of these 10 to the negative percent values when we're talking about things, we said, you know what? We're going to all come to an agreement. We're going to make something. We're going to call it the pH scale. And we are going to take the absolute value of the exponent so that we didn't have to mess with exponents, negative exponents. So the scale was basically the whole value of a 10 to the negative exponent. So water has a pH of 7, not 10 to the negative 7. So 10 to the negative 7% H plus is a pH of 7. And it makes it a lot easier to work with and handle. Okay, so this is where you want to indicate what does your pH stand for. All right, so on our next piece here, we want to read through, and then we have a couple of questions. So it says, when some substances dissolve in water, they break up into ions. A compound that releases a hydrogen ion, a proton, when it dissolves in water is an acid. Bases are compounds that remove or accept hydrogen ions from a solution. A solution's acidity or hydrogen ion concentration is measured on the pH scale. An acid has a low pH, a pH of 0 to 7, and a high hydrogen ion concentration. Because remember, it was 10 to the negative, right? So those lower numbers is actually a bigger decimal. A base has a high pH, 7 to 14, and a low hydrogen ion concentration. Organisms must maintain a stable pH, and even a small change in pH can disrupt many biological processes. Pure water has a pH of exactly 7. So we want to figure out, what does an acid release when it's dissolved? Okay, so that's going to be up here in the first two sentences. On our next slide, what does the base remove when it's dissolved? That is here in kind of our third sentence. What is a solution's pH measuring? That is going to be here in sentence number 4. Now, for this one, using our numbers here in sentence 5 and 6, you want to draw a pH scale using numbers. So we should have a number line, 1 to 14, because our numbers are from 0 to 14. That's where our numbers are. We should also have a notch there for 7, because 7 is one of the other numbers that we're seeing here. And we want to label what part is an acid, what part is a base, and where is the neutral. Okay, so using the second half of this paragraph. Now, going back, and you can always go back and reread and look at some of those previous slides, you want to place the red dot on the beaker with acid, the green dot on the neutral beaker, and the blue dot on the beaker with the base. And if you look, there is different numbers of the OH minuses and H pluses in each one of these beakers. So if you need to, you want to come back and look at the slides previous to remember which ones have more or less of the H plus or the OH minus. Next, we have a kind of practical application problem. So a student mixes strawberry Kool-Aid and water. A pH meter is used to measure the pH of 5.4. What kind of solution would be strawberry Kool-Aid? So you can go to your pH scale you made here and look for that pH number of 5.4. Where would it fall? Would it fall under an acid or a base or neutral? Then we add Alka-Seltzer to the Kool-Aid and stir. The pH meter now reads 8.3. What do you think was released by that Alka-Seltzer tablet to cause that change? Think back to when we have our different things here. What could have been released in order to cause that change for it to go up to 8.3, which would make it more of a base now? Now, once we've answered all of these, you will want to do your next foldable. So this is what the inside of the foldable looks like. Basically, we want to have our definition, our characteristics, and examples of each. So under acids, all the way to the left, our definition is a molecule that donates an H plus ion and has a pH of less than 7. The way you can tell something's an acid is it tastes sour, it releases those H plus ions, and it feels sticky. If you had some in your hand and you kind of rubbed it between your fingers, it would have a sticky feel. Many of you have experienced this with the citric acid granules that's on like the Sour Patch Kids or the Sour Straws. That is actually not sugar. That is citric acid, and it still has that kind of sticky feel. Some examples here are orange juice, vinegar, all of your sodas. These are all acids. Now, if I jump over to the other side, all the way to the right, the bases. Our definition of a base is a molecule that can remove an H plus ion from a solution. So it's kind of acting like a little vacuum of those H plus ions. Sometimes it does this by releasing hydroxide ions, those OHs, so they can react with the H pluses. And it has a pH of more than 7. The characteristics here is they taste really bitter, they release OH ions, and they feel slippery. If you've ever had like soap or cleaned with bleach but without having rubber gloves on, you'll notice that real slippery feeling. The examples here are most of our cleansers are bases. Milk is a very mild base. Soaps, these are our bases. Now, in the center, we have our neutrals. So For our neutrals, a solution that's neither acidic or basic, it has a pH of exactly 7. So not even a tiny 6.999 is an acid. 7.0001 is a base. It has to be exactly 7 to be truly neutral. Now, in practice, as long as it's pretty close to 7, we consider it neutral. But to be exact, it's when it's exactly there at 7. And that means it has the exact same equal amount of H plus and OH minus. Now, when we have an acid or a base, we can neutralize this, and we call that neutralization. And this is when an acid and a base work against each other, they react, and they end up forming salt compounds. Now, sometimes it's like sodium chloride, which is table salt, but sometimes it's things like potassium chloride. Sometimes it is some of our other magnesium chloride, are some of our other salts. So like the salts we put on, like the road salt, when you have some of the cleanser salts, these are ones that like you don't want to eat them, but it is because an acid and a base reacted. Now we have two kinds of indicators. pH paper is the one that you're pretty much going to see 99% of the time. Litmus paper, however, is the like old-fashioned version of pH paper. And litmus paper is using these natural indicators. So if you have ever had like the red onions that are really kind of purple looking, red cabbage does this. Some of the like the violet flavored teas, they all react to pH. And what happens is we can actually make litmus paper, which is basically filter paper that has this indicator that happens in nature. And if you put acid on it, it turns this bright red. Really, it's closer to like a hot pink color. And if you add a base to it, it goes to like a bluey green. In fact, if you have like red onions, if any of you have ever had some of the like quick pickle red onions that are really popular in kind of middle South American cuisine, where you have the red onion sliced and they add the lime juice to it, you'll notice that instead of them staying that purpley red color, they go to this like bright hot pink color. That's because of the acid in the lime juice. Now, if you took some red cabbage juice or red onion juice and you added like a soap or a base to it, it actually goes and turns like this bluey green color. And that tells you that it's a base. So these are referred to as litmus papers. You will sometimes still see them. You'll sometimes see them referred to on tests and in literature, but that's what it is it's the old kind of version of our pH scale. Now, for our exit ticket, are acids or bases more dangerous and why? So I want you to take a moment, think about it. Now, guys, here, remember, acids are just positive charges. Well, you're mostly neutral, but not because all of your molecules are neutral, but because you have about half positive and half negative molecules. Well, if I put an acid on my hand, right, a strong acid, it's a really lots of positive charges. So what it's going to do is it's going to rip out any negative charged molecules out of my hand, which is about half of them, and I'd see my skin dissolve and I'd get a chemical burn. But if I were to put a really strong base, bases have a lot of negatives. Well, it would rip out all of the positive charged molecules. Now, it wouldn't be the exact same molecules. They'd be the opposite set, but it would still take about half of them, and I would see my skin dissolve. They are equally dangerous. The reason why we hear more about these acids than bases is honestly just popular media liked the name acid more than base. Bases actually tend to be more dangerous because people don't think of them being dangerous. And so we get more chemical burns from inadvertent using bases, whereas if we see the word acid, people are a lot more careful with them. Whereas when we see a base, we're not always as careful. So bases are things like bleach, which absolutely causes chemical burns, right? If you had just straight bleach and left it on your hands, like your hands will ache. If you've ever had to do like a big deep clean, spring cleaning type thing, and you've been using bleach all day, like your hands will ache, and that's from a mild chemical burn. And that's with really like diluted bleach. Like the jug of Clorox you get is only